Today we're going to be practicing our second derivative test, okay? So again, the second derivative test tells us our function's concavity. It also gives us our points of inflection. So it's asking us to determine the open intervals in which the graph is concave up or concave down. So basically, you start by finding the second derivative, because that's what tells us concavity. So you have to first find the first derivative. So 5x to the fourth minus 5 is the first derivative. But we need concavity, so we need the second derivative. So you get 20x cubed. So just like a first derivative test, you need to find your critical points of your second derivative by setting equal to 0, which means x equals 0 is my critical point. Okay, so this is a possible point of inflection. Okay, so then we create our number line. 0 is a 0. So this is a 0 of my second derivative. Now I pick values on either side, like negative 1. When I plug negative 1 in, negative 1 cubed is negative, so you get negative on the side. Or positive 1, which gives me positive. So basically this function, the concavity, since it's concave down on this side because the second derivative is negative, and here it's concave up, or the cup opens up here because it's positive. So that's the way my function looks. My intervals, my open intervals, so it is concave up when x is bigger than 0. It is concave down when x is less than 0. It's that easy. Okay? So just like a first derivative test tells us where it's increasing or decreasing, or maximums and minimums, the second derivative tells me where my function is concave up, concave down, or in this case, 0 is a point of inflection because it changes from concave down to concave up. Okay? So determine the points of inflection and find the open intervals on which the graph is concave up and concave down. So this is basically what we did on the last one. Well, the difference is that to find the derivative, we have a little more work to do. So we still need to find the second derivative. So we got to take the derivative of this. So derivative of x is 1. This is x minus 4 cubed plus x times the derivative of the second one. Since we're doing product rule here, we get the derivative of the inside, which is 1, times the derivative of the outside, which is 3x minus 4 squared. Okay, so let's simplify this a little bit. So we get x minus 4 cubed plus 3x times x minus 4 squared. Like that. Okay, that's my first derivative. Now we got to take and find our second derivative. So f double prime of x. Same thing, derivative of the inside, we got to do some chain rule, times the derivative of the outside, which is 3x minus 4 squared, plus, and here we got to do product rule again. So the derivative of 3x is 3, x minus 4 squared, plus 3x times the derivative of this, which is 2x minus 4. Okay, so let's simplify a little bit, because this is our second derivative. So we get 3x minus 4 squared plus 3x minus 4 squared plus 6x x minus 4. Okay? Simplify a little more. We have 3 plus another 3, so this is 6x minus 4 squareds plus 6x x minus 4. So we got to set this equal to 0 now. Set this equal to 0 and solve for x. Well, the first thing you always do when you do solving for x is you take out your greatest common factor. And if you look between these two things, our greatest common factor is 6 times x minus 4. So we're left with, in this one, x minus 4, plus, in this one, I'm left with just this x, because this x minus 4 has been taken out. Going to get this minus 4, and here we've got x minus 4 plus x, which is 2x minus 4, equal to 0. So we got a little more algebra to do, but basically our critical points are 4, and when you solve this, you move the 4 to the other side, divide by 2, and you get x equals 2. Those are your two critical points. Okay? Now, we do the same thing we did before, set up our number line. 2 and 4. Those are my zeros. Okay? Now, pick numbers. We pick 0. I'm going to use this one right here. It's in its factored form. So I plug in 0, I'm going to get 6 times negative 4 times negative 4, which means this part is positive. Then I'm going to plug in 3. When I plug in 3, I'm going to get 6 times negative 1 times positive 2. So this is negative here. And then when I plug in 5, I get 6 times 1 times positive 6, which is a positive there. Okay? Which means my concavity, this is concave up, this is concave down, that is concave up. Which means 2 and 4 are points of inflection. So I have points of inflection, sorry, POI, at 2 something and 4 something. And we'll find those in just a minute by plugging them into the original equation. So we need to find f at 2. When you plug in 2, you're going to get 2, and that's 2 minus 4, which is negative 2 cubed. So you get negative 2 cubed, which is negative 8 times 2, which is negative 16. And f at 4 is going to be 0. Because 4 minus 4 is 0, 0 cubed is 0, 4, 0. So those are our points of inflection. 2, negative 16, and 4, 0. And our concavity, our function is concave up from negative infinity to 2 in union with 4 to infinity. And it is concave down only between 2 and 4. And that's our concavity. Okay, so we had a little more work to do, some algebra to deal with, but other than that, pretty simple. Okay, so for the last one, same thing. For the following function, find the relative extrema using the second derivative test. So now we're not going to be using or finding concavity, we're going to be finding maximums and minimums, but we're going to find them using the second derivative test. So I still need to find the second derivative and the first derivative. So find the first derivative. So I get negative 3x squared plus 14x minus 15. There's the first derivative. Second derivative is going to be negative 6x plus 14. Okay? So first thing we do is find our critical points for our relative extrema. So we got to use the first derivative to find that. Okay? So set this equal to 0. So I'm going to use the old slide and divide technique. So I'm going to slide the negative 3 here. So I get x squared plus 14x plus 30. So 1 and 30, 2 and 15, 3 and 10, 5 and 6. Oh, I misdid it. This should be 45. Should be plus 45. And that's why it didn't make any sense. So 1 and 45, then it would be 5 and 9. So we're going to use 5 and 9. So x plus 5 and x plus 9. Okay, but then what we have to do is we got to divide by -3 on both of them, since that's what we multiplied by. And since here we're going to get x, and positive 9 divided by -3 is -3. But here we cannot, so we slide it back and we get -3x plus 5. And does it work? Sure does, because -3 times -3 is positive 9 plus 5. So this is my solutions. So basically my solutions are x equals 3 and x equals -5/3. Or positive 5/3. Okay. So those are my critical points. Now, I'm going to use the first derivative test to test them. So now I'm going to find the zeros of my second derivative. So move the 14 over, so you get -6x equals -14, divide by -6, divide by -6. So you get x equals 14 over 6, or 7 over 3. Okay, so that's my second derivative test that I'm going to use. So I put 7 over 3, that's my 0. And 7 over 3 is basically 2 1/3. Okay, so then I'm going to use this, and right here I'm going to put 3. And when I put 3 in here into my second derivative, -6 times 3 is -18, so this side's negative. And then here I'm going to put that 5/3. When I plug in 5/3, you're going to get -30 over 3, which is -10 plus 14. This side's positive. So this side is concave up, and this side is concave down. Which means my critical points, using that, my critical points at x equals 3, right here, is a relative maximum. Because the concavity here is concave down, that means that maximum point is up there. And x equals 5/3 is a relative minimum because my concavity is concave up, which means that if this is a critical point and it looks like this, that is a minimum. And that's how you use the second derivative test to actually find your critical points.